Hello, welcome to the course UEC 001. In the previous module, we have discussed the applications of CMOS technology, and we have designed fundamental gates and the universal gate, NAND gate. Okay, so let's see how to design another universal gate, that is the NOR gate, with the help of CMOS logic. Okay, so let's see implementation of NOR gate using CMOS. So again, before the implementation, let us first discuss the basic logic of NOR gate. This is the symbolical representation. I am taking two inputs, A and B. However, it is not limited to two inputs only. Inputs can be increased and accordingly circuit can be designed. So if my inputs are A, B, output is Y, then the mathematical representation says that Y will be equals to A or B whole complement. And the relation can be formed in a truth table, as we have considered two inputs A, B, output is Y. So there will be four combinations 0, 0, 0, 1, 1, 0 and 1, 1. So over here my output becomes, now I can check if 0 plus 0 is 0 itself and complement is 1, 0, 0 or 1 is 1 and its complement is 0. So if anywhere is 1, that means its complement will be 0. So this will be the truth table. We have to verify this table for the circuit. Now we have to design a circuit which should satisfy this table. And for the simplicity, I am marking these two cases. Case number 1, when both inputs are at 0, 0 cases, and case number 3, when input A is 1 and output and B is 0, output is 0. Okay, so let me draw the circuit and then, so in this case the PMOS will be connected in series configurations. So I'm saying that giving input A over here to another PMOS which is connected in series, input B, VSS, transistor Q1, transistor Q2, and the two NMOS will be connected in shunt configuration. Input A, suppose this is my Q3, input B, and suppose this is my Q4, and their source will be combined and connected to the ground potential, and we will measure output from here. This is my output terminal. So this is the NOR gate realization. This is my NOR gate realization using CMOS, and this is for two inputs. However, if suppose there are three inputs, so what we have to do? We have to include one more PMOS over here in the series combination and one more NMOS in the shunt configuration. So referring to the case number 1, when both inputs are at 0, 0, we have to verify that my output should be equals to 1. So considering the first case, if A and B both are at 0 logic, so now I can refer. If both are at 0 logic, Q1, Q2 both will be on. So Q1 and Q2 both will be on. At the same time, Q3 and Q4, as inputs are 0, these two will be off. So Q3 and Q4 will be off. So let me draw the equivalent circuit for the ideal scenario. These two transistors which are connected in series configurations, these are on, so replaced by a closed switch. Transistor Q1, transistor Q2, considering the case VSS equals to plus 5 volt, logic 0 means ground potential, and these two parallel transistors will be replaced by open circuit as both are off. Transistor Q3, transistor Q4, and now you can check the output. So no current can flow through this open circuit. That means this lower segment is decoupled to the output. Considering the ideal cases, if drop across the two transistors is 0, this 5 volt entire voltage is available at the output. So I am having logic 1 at the output, and now you can check. I have to verify that my output should be equals to 1. So we have verified. Now considering this case, when A equals to 1 and B equals to 0. So considering the second case, if A equals to 1 and B equals to 0. So let me write the condition first. If A equals to 0, that means Q1 is on. A1 is 1, so my Q1 will be off as it is PMOS, and Q2 will be on as its input is 0. On the other side, my Q3 will be on and Q4 will be off. And now you can check the circuit representation. So my Q1 is off, Q2 is shorted in this parallel side, Q3 is on, Q4 is off. This parallel assembly is connected to ground. I'm taking output from here, plus 5 volt. This was Q2, Q3 and Q4. So now I can check as these two are in series, okay, and there is an open circuit, so no current can flow through this path as there is an open circuit. These two transistors are in parallel, so even though Q4 is open circuited, a alternative path is available through this transistor Q3. So my output is directly coupled to the ground through transistor Q3. That means in this situation, my output will be at logic 0. So you can check, we have verified for this case and my output is 0. So we have verified the implementation of NOR gate with the help of CMOS. Okay, so let us see the implementation of one more fundamental gate, implementation of OR gate. Implementation of OR gate using CMOS. So again we will start with the basics of digital electronics. The symbolical presentation for OR gate is, if there are two inputs, output is Y, this is the symbol, and the relation is Y says that A or B, or with the traditional algebra A plus B. Intuitively this can be designed using a NOR followed by NOT gate. So my inputs are A and B. I'm seeing output over here A or B complement this supplied input to the NOT gate. So output at this side will be A or complements whole complement, which is nothing but my A or B. So this is the logic we will use over here. Okay, this is my NOR followed by NOT is nothing but OR gate realization. So we will use this logic, and for final verification we need a truth table. So my input output logic, inputs are A, B, output is Y, combination 0, 0, 0, 1, 1, 0 and 1, 1. and you can check if any input is 1, output is 1. If both inputs are 0, my output is 0. So this is the truth table for OR gate, and we will use the same logic. So we have to draw first NOR gate, then followed by a NOT. Our purpose will be solved. So let's see the circuit diagram. So let me draw first NOR gate, and for that we require two PMOS. So as we require the two inputs, therefore we require two PMOS in series configuration. Input A and B supply VDD, and then we require two NMOS connected in parallel configuration. Input A, input B, and this is grounded. So this is my NOR gate, and I can check its output, and I have to connect its output to the input of the inverter. This is grounded, and this is connected to VSS. In fact, I'm saying choosing the same VSS over here. So suppose this is my transistor T1, transistor T2, transistor T3, transistor T4, transistor T5, and transistor T6. Final output I am taking from here, from the two drains of transistor T5 and T6. This is my overall output, and this is my NOT gate, and this overall assembly is my finally OR gate output. So I will receive the OR gate output from here. So even I am marking over here, I will receive A or B complement. Across here, I will receive A or complement's whole complement, which is nothing but A or B. So as far as the proof concerned, uh, I am keeping left the proof to the viewers with the knowledge they had gained from the uh, previous module and the contents they deliver in this module till now. They can easily verify. Okay, so thank you very much.